All right. So our next speaker is Yuguang Chen, and he will tell us about the Metallicity of Quaternary 71.
Cool. Thank you. Thank you all for waking up in a cloudy morning to listen to my talk. I'm Yuguang Chen, a postdoc at UC Davis, and here are the people I work with over there. Carter Jones, who's back in the room, and Ryan and Aaron, who unfortunately are not here. So today I'm going to talk about the keyword being accurate. So how to accurately measure the gas phase metallicity in one of our very special system, Macarian 71, using KCWL and SOPIA as a preview for JWST and ALMA at very high redshift. So I believe you all have seen at least this one. Speak up. Oh, does this work better?
Turn on.
Okay, test. Cool, thank you. So, so I'll just stick over here then. So I believe you've all seen this figure. So that's the JWST first release, the early release science spectrum. And so it's very apparent that James Webb can detect O3 emission at very high redshift. I believe it's over redshift 8. And it also has been observed by ALMA that the far-infrared O3 emission, particularly the 88 micron, has been detected at redshift near 8 as well. So our interest here is to accurately measure the metallicity. And this has been on the astronomers' wish list for a very long time. There are many reasons. I just listed a couple here. So for example, we want to analyze the redshift evolution. And there are multiple, as I said, mentioned in the earlier slide, there are multiple methods measuring the O3 emission lines in different wavelengths. And also, if you are interested in measure the efficiency of the outflow and inflows with respect to star formation rate, for example, the metallicity will be very important to compare with. So in the bigger picture, the measuring the interstellar medium's metallicity is very important to us. But in different gas, there are multiple different problems with measuring metallicity very accurately. But for ISM, if you're caring about measuring in the emission line spectroscopy, the largest systematic problem is what we call the abundance discrepancy factor. So here is just the metallicity measured, OH metallicity measured with different emission lines. So y-axis, these are from the collisionally excited lines. So famously O3 507, for example. The x-axis are measured from much fainter, but usually 2 or 3 orders magnitude fainter than the collisionally excited lines. These are the recombination lines. So you can already see there's a systematic difference between the two methods, and it's up to a factor of 2 difference. So that's huge. If you want to compare to simulations, for example, when compared to measurements from other methods, for example, the CGM compared to the metallicity from stars, this will become huge because factor 2, that's a lot. So the common explanation of this discrepancy is that there's temperature distribution in the gap. So temperature fluctuation, for example, can potentially explain this discrepancy. The reason is that what I showed here, the optical strong lines, the collisionally excited lines, are very dependent to temperature. So you are naturally biased to measure gas, to see more gas from the high temperature. And so the emissivity will be over-predicted and the metallicity will be under-predicted. And it's also because that, so these lines are from these lines are from the recombination lines. So it's also because the low dependency of the temperature from the recombination lines are sometimes considered more accurate. So this axis is considered less accurate, this considers more accurate. What you can also see here is that if there are these far-infrared emission lines, the O3 52 microns and 82 and 88 microns are actually very similar dependent to temperature as the recombination lines. So goal here is to use the infrared lines to test whether the temperature fluctuation is really the cause here. And that brings us to our very special target, the Markarian 71. So this is an HST image from previous studies. So you can see very nicely resolved and very nicely studied before. It's a high-Z galaxy analog. There are many properties that resembles high-redshift galaxies. The only thing that doesn't is because it's very low mass. It's a very dwarfy galaxy, 10 to the 5th solar mass system. But aside from that, the star formation rate, the temperatures, the metallicities are all very similar. It's also very nearby. So that's why we think it's very special. And we took a lot of from multiple instruments, many observations. So most notably from KCWI. So this is the KCWI field of view on this object. We took two in two different methods. So one are very short snapshots because we want to capture these collisionally excited lines. Those are super bright. So 5-second snapshots, we still saturated 5007. So we left the two other lines. But also we want to capture the very faint recombination lines. So that's why we took over 1 hour to fully use the KCWI sensitivity gain here. So we took very long exposures on these. And we also have SOPIA 50OS to capture the far-infrared 52 micron and also the archival virtual data for the 88 micron. So the reason we want to use all of these instruments, the most important factors, because they are all IFE spectroscopy. So it's very important for us because we're matching between 3 different instruments at very different wavelengths. We want to conduct very accurate PSF matching. So that's why the spatial resolution, the spatial capability is very important for us. So here is just one example where we try to match those 3 4959 with the SOPIA DBLS data. And here are the extracted spectrum. So these are the KCWI spectrum in full wavelength display. The recombination lines, you can see the recombination lines are well detected. The KCWI H-beta, KCWI O3, and this is from the SOPIA. You can see the O3 is also well detected, and this is from the Herschel PAC. So here is the result. We did very careful flux calibration error analysis, and also did very careful extinction correction errors analysis. I wouldn't bore you with the details, but if you're interested, I can provide you with some backup slides later. So here, y-axis, we're showing the temperature measured from this system, and the x-axis, the density, electron density. And what really surprised us, this really surprising result, is that, remember, we always consider the recombination line as the more favored, more accurate metallicity measurement. So because the far-infrared, the 52 micron and the 88 micron are also not temperature sensitive, we would expect, if the temperature is at play here, the temperature is really offsetting the abundance discrepancy between the two traditionally measured in optical, the recombination line, like collisionally excited lines. If the temperature is really at play here, we would expect the far-infrared detection should be consistent with the recombination line. But instead, it's very far from it. And also, what's surprising us is actually consistent with the collisional lines. So this is a very surprising result, and we want to test this very rigorously. One test is we just remove completely the extinction correction, because the extinction correction is actually one of the largest systematic error in your analysis. So we just completely remove that process. And what's special for this system is that this system has very small extinction overall. So even if we remove it, you can still see that this far-infrared is not consistent with the recombination line at all. So what does this mean? This means the TE may not be the main cause. The temperature fluctuation may not be the main cause of the abundance discrepancy. And this basically raised the question of whether the recombination line metallicity is really accurate. And this is a huge problem because when we push for very high redshift over 8 galaxies, we really need to understand which one is the accurate. So possible explanations. For this particular system, we built a model that can explain the discrepancy resistivity variations. So if we introduce, the gray lines here are the observed flux over the model fluxes, and for different line flux measurements, the gray ones are just a single phase, the typical method. And when we introduce more variability to the second phase of gas, we can gradually bring the models to close to the observed fluxes. So this could be an explanation here, and you can see with 2-phase models we can actually predict these observed lines close to the model. But then we have some preliminary results with the UV flux measurements done by graduate students in our group, Eric Hunsinger, and also because we have KCWL, so we can actually analyze the spatial variations of it. And that doesn't seem to support us that density is at play here. So metallicity variations, possibly, and also whether it's there are some fundamental issues between the collision cycle lines and the recombination lines. We don't know yet. So just give you a little bit bigger picture. You might think this particular system is just special, right? Because I only showed you one system, but we actually have a survey I can't say there are a lot of galaxies. The yellow points are the ones that we have. So we have about 6 or 7, depends on, so unfortunately, because SOPIA is being shut down, so we can't observe them all. So we have 5 or 6 galaxies. Here are just 2 examples. So you can see that it's either consistent with the collision excited lines or it's in between. They are never consistent with a recombination line. It's also very surprising to us. So future, we really love to have the KCRF. One reason is because we can then observe the nitrogen-2 emission, and the far-infrared nitrogen-2 emission and the optical will be very interesting to compare with. And we dive into the archival data from Herschel and SOPIA, and we think we can observe with between 20 to 60 more galaxies. And the future is also, of course, JWST and ELMO. So I'll leave the summary here and take questions. Thank you.
All right, questions at the very end, you hit the point that I was going to ask, which is what KCRM is going to do for you. So can you talk a little bit more about that?
Sure.
Repeat the question.
What KCRM can do. So the thing I mentioned here, that's one of our most our wish list for a long time is because this abundance dispersion has been detected not only for O3 but also for nitrogen-2 and carbon-2, for example. Currently, we can only test it on O3 because that's the KCWL spectral coverage. But we would really love to have the nitrogen-2 because that provides an independent test. We can, although we can't really have the recombination lines possibly, but then even compare the systematic difference of far-infrared emission and the nitrogen-2 6584 will be very interesting for us. And also for the entire sample, if we can do that possibly.
Do we have questions?
No.
Oh, okay.
I think, well, some from same region.
That is true. Oh, so the assumption here is that all of the emission lines come from the same region. Whether that is true. So there's something here, at least for the O3. So that's actually one of the reasons I forgot to mention, but it's very important is that the abundance distribution has been tested, whether it's caused by temperature fluctuation, have been tested on many multiple lines, but then they're all tested on different species, not consistently on one. So the interesting thing about this work is that we tested on only oxygen plus. So the O2 recombination lines is from oxygen plus doubly ionized oxygen, and the O3 collisional lines are also from the same gas. So that's why this test is very interesting to us.
Okay, and you will ask a quick question. So now let's thank our speaker again.